The ARNO testbed, situated in the CNIT PNT lab in Scuola Sant'Anna premises in Pisa, Italy, serves as an innovative hub for advanced networking research. Jointly managed by CNIT and Sant'Anna University, this dynamic testbed integrates access, metro, and core networks, fostering collaborations in emulated data centers and participation in numerous international research projects. Renowned for its excellence, the testbed has garnered trust from both industrial partners and globally recognized research groups. Its establishment and expansion have been made possible through research grants from leading companies, including Ericsson, Trenitalia, Schindler Group, Telecom Italia, and others. Over 2 decades, it has played a pivotal role in EU-sponsored projects on optical networking during FP6, FP7, and H2020, supplemented by national and regional projects. Originally conceived as an optical networking testbed, supporting IP over WDM environments, the testbed evolved to encompass various telecommunication network segments. It now includes metro, cloud/edge segments, and next-generation RANs. At the packet level, it incorporates software-defined networking-enabled devices like OpenFlow switches and controllers, progressing to SDN data plane programmability with programmable devices such as P4 switches, P4 smart NICs, and data processing units, DPU. Recent enhancements cover the access segment with Wi-Fi 6, LTE, and 5G proof-of-concept infrastructures. Diverse user equipments, including drones, autonomous mobile robots, and rovers, have been integrated. The evolution of network softwareization and the rise of cloud computing prompted the testbed to include IT infrastructures. This expansion spans computing servers dedicated to virtualization, up to small data center infrastructure emulation, featuring 2 racks of servers with varying computing capabilities, including GPUs for running AI-based algorithms. The testbed is housed in 2 adjacent lab rooms, providing a comprehensive and versatile environment for cutting-edge networking research. Our testbed encompasses diverse telco plus IT segments, reflecting the forefront of technological innovation. These segments include long-haul transport optical networks, metro FlexGrid disaggregated optical networks, aggregation, featuring routers and of switches, access, incorporating PON and 5G RAN, cloud/edge nodes and interconnects, wireless mobile terminals. The primary objective of our testbed in DESIRE6G is to experimentally validate concepts, ideas, and research topics explored by CNIT and Sant'Anna University researchers in collaboration with the other partners of the project. This involves leveraging state-of-the-art technology and telecommunications/IT platforms. Moreover, the testbed has a rich historical mission, facilitating broader interconnections with other distributed testbeds to create expansive sandboxes. This mission has been achieved in numerous European projects, wherein the testbed seamlessly connected with others using various protocols such as IPsec, generic routing encapsulation, OpenVPN, and border gateway protocol. This collaborative approach continues with the DESIRE6G development, integration, testing, and validation activities. The integrated testbed we're building is open to partners in 2 ways. 1. Remote access for the integration, testing, and validation of system components. 2. Peer-to-peer access, fostering interconnectivity with other DESIRE6G testbeds, thereby realizing federated testbeds. This openness invites collaboration and innovation, propelling our research to new heights. The testbed has the capability to provide different edge nodes, for example, 3 nodes emulating 2 edge and 1 cloud data center. The DESIRE6G components will be integrated inside each node on top of existing IT/network resources. Moreover, the vertical app, the augmented reality chained application, will be hosted as service applications that may be instantiated by the orchestrator. The Programmable Data Plane Network, including P4, Data Plane Development Kit, DPDK, and Extended Berkeley Packet Filter, eBPF, will be exploited for both intra-edge networking and inter-edge connectivity. Fixed terminals will be attested to given edge nodes, while mobile terminals will be connected using distributed RAN functions exploiting functional split that may be either centralized in a single edge, for example, distributed unit plus centralized unit plus radio access network intelligence controller plus core network, namely DU plus CU plus RIC plus CN, or distributed across different edges, depending on the required 6G deployment scenario. In DESIRE6G, we have considered to include a close participation to the testbed activities by specific partners. NVIDIA participates as a system integrator with special focus on the programmable switches and DPU resources available in the testbed. Accelerant participates as a system integrator of the 5G radio stack, complementing the resources already available in the testbed with their own software stack, RIC, CU, and open source DUs. University of Catalunya participates as integrator of the multi-agent system, in charge of performing end-to-end service monitoring resorting to artificial intelligence algorithms. Nubis participates as integrator of the DESIRE6G service orchestrator. Finally, University of Amsterdam participates as P4 data plane software integrator with special focus on in-band telemetry implementations. The main goal achieved by the integrated testbed is to demonstrate perceived zero latency at the app level resorting to the DESIRE6G innovative concept of pervasive monitoring. The demonstration includes an augmented reality application that takes advantage of application-level resilience based on split learning. Drones and headset terminals are capturing images and each one learns a model before sending it to the edge. Models are combined with others coming from multiple sources and sent back to the terminals for better prediction. Such a combination requires strict delay from the local model computation until reception of the combined model. Therefore, the end-to-end latency is constantly monitored by the terminals, and it is combined with other data sources, like the received RF signal and geolocalization-based estimated trajectory. A module in the application is able to combine such heterogeneous data to predict near-future key quality indicators, KQI, degradations that would impact the accuracy of the model predictions at the terminals. In such case, the application can change its topology real-time for application perceived zero latency. This use case will be demonstrated at the ARNO testbed. AI-driven local decisions will be fed by network and computing status info as subscribed telemetry services. Context awareness through local AI will also enable autonomous forwarding decisions among the multiple available connectivity options, including the capability to exchange AI models through MAS communication with the network infrastructure and to predict mobility conditions, e.g., edge/cloud migration. The P4-based pervasive telemetry including telemetry, supporting packet augmentation with latency, geolocalization, and QoE will be supported, to provide the network with the capability to predict in advance any degradation and coordinate autonomous decisions taken locally by the device to adapt the network in advance.